Good evening, good afternoon, good morning. I don't know when you're going to be watching these videos, so I'm going to take care of all of that. Before we get started in sections 12.1 and 12.2, I just want to briefly do a recap of what is mechanics. So these next couple of slides might look familiar. We saw them in statics. Mechanics involves the rest or motion of bodies that are subjected to actions and forces. So we have the study of rigid body mechanics, and rigid body mechanics includes statics, bodies at rest, and dynamics, bodies in motion. So when we're looking at dynamics, we can consider the car or the airplane or the rocket just as a particle. We're not looking at the individual deformations of the system itself. So this could also be called particle mechanics. Statics and dynamics are particle mechanics. Many of you may have also had strengths or are currently in strengths and materials right now, and that's the mechanics of deformable bodies. So that's where you look at the deformation that occurs. It looks at shear stress, it looks at normal stress, shear strain, normal strain, all of those things. Dynamics is just the second part of statics. It's all rigid body mechanics. It's all particle mechanics. We just now will be looking at things that move. So if we are looking through at a slide of how that looks, again, this slide should look familiar. We can consider it to be a particle. We're either at rest or we are in motion. That wagon could just be a particle moving. In strengths, you start looking at that deformation. There's also the mechanics of fluids, and many of you might be taking fluids now or next semester. So I'm going to escape out of that. And we're going to go back now and start with sections 12.1 and 12.2. So we're going to be looking at rectilinear kinematics. There are two different groups of material that we will be learning about in dynamics. The first is kinematics, and kinematics is the dynamic of motion. So we don't look at how did the object become in motion, why is it moving. You can think about free flight. We're not looking at the force that causes the football to move. If we're kicking a football, we are looking at immediately after the force has been applied, that motion that occurs. So kinematics is we're not concerned with the force. We're just in motion. Kinetics, which will be chapter 13 and on, that is where we start looking at why is it moving? What's the power involved? What's the force needed to make this happen? So chapter 12 is super important because we will be using this information for the rest of the semester. Okay, so when we're talking about rectilinear kinematics, we're going to be looking specifically just at a straight line motion. Again, it's without reference to force, and we're going to learn about the association between position, velocity, and acceleration. And me, with my strengths background, I like to think about it as the same relationship that we have forces, shear, and moment. If we integrate the force, we get our shear diagram. If we integrate the shear diagram, that's finding the area under the curve to develop that moment diagram. It's the same thing here. If we look at acceleration, velocity, and position, you can see that just like force, shear, and moment, they increase in order of curve. So the very first definition we have is position, and we are going to call position S. It's defined as S in the textbook, and we're going to go with S. So when we're looking at position, we're going to have an initial position, which is S, and another position, maybe a final position, S prime. And so we can then determine what's going on between point A and point B. Okay, so it's a vector quantity. It has both magnitude and direction. As we're looking at definitions, delta S is displacement. So anytime you see that triangular delta, that means a change in, whether it's delta temperature, change in temperature, delta L, like you might use in strengths, change in length. We have change in position. The car is here, now the car is here. So the displacement is the final position minus the initial position, okay? Or S prime minus S. We could also look at distance. So in this scenario here, we can see that the car has traveled. Maybe I left my house and then I went to Aspen Coffee to get a coffee, and then I went to the university. So my starting and stopping position are my house and the university, but I kind of made a little trip there in the middle. So the distance is the total distance traveled that my car has gone through. It's the mileage I've put on my car. The displacement is just where I ended up, the university, minus where I started my house. So make sure you understand those two. Displacement is final minus initial. It's delta S. Total path is the distance traveled. Okay, so here's just a quick example. In this case, what is our displacement? So remember, displacement is final minus initial, so it's going to be 10 minus 5, which is 5 meters. What about our distance? Well, our distance is the total length of the path. We have 20 minus 5, 20 minus 10. So we end up with a total distance of 25 meters. So this brings us to this type of a scenario where what is the displacement here? I got in my car, I drove to Aspen, I had to come back home. I forgot something. So I'm starting and stopping at the same place. My displacement in this case is final minus initial is 0. So you can have a displacement of 0. But our distance, we still have a 30-meter path that we did travel. So again, so your displacement can be 0, and you could still have a distance of lots of miles. Maybe you go on vacation. I started at my house. I drove to Alabama. I came back to my house. My displacement for my vacation was 0. However, I put thousands of miles on my car. Okay. So now let's look at velocity. So velocity is v, and velocity is the displacement over time. So if you're going back and thinking, displacement is delta S, it's final minus initial over the amount of time that's been spent. So that's our average velocity. It is the change, that delta, that change in velocity over the amount of time. So if you think about displacement, okay, if you have 0 displacement, but I took a week to go somewhere and then come back, I could have a 0 velocity average, which sounds kind of weird. We're going to be making sure that we show positive and negative motion, especially when we get to forces. So maybe I'm going to have the particle's going to the right. If the velocity is going to the left, it just means it's working against our motion. We are slowing down. So instead of calling it a negative velocity, I'm going to show it in the opposite direction. Maybe I'm slowing down to come to the stop sign. So I'm still moving forwards, but my velocity is acting against me. Okay. So we also then can look at displacement over time. We'll get to instantaneous in a minute. So our average speed then, what is my speed? That is the total distance over time. So we have average velocity, delta S over delta T, average speed, entire displacement over time. So let's look at those same examples again. So what if it took us 10 seconds for this particle to go from A to B? So my average velocity is displacement over time. So I have 5 over 10 seconds. So I have an average velocity of 0.5 meters per second. My average speed is the entire distance divided by that time. So my average speed is 2.5 meters per second, which brings us to what if we start and stop at the same spot? I could have a 0 displacement, 0 meters per second for my average velocity. However, my average speed is going to be the entire path over the amount of time that it takes. Okay. So, and again, we're going to get to instantaneous shortly. That's going to involve more math. So acceleration, then what is acceleration? It is our change in velocity over time. So if I have a change in position, delta S, final minus initial over time, I have velocity, initial velocity, final velocity. I'm going to take final minus initial over time. That's how I get to acceleration. It's that change. We'll talk about instantaneous, which would be like right at this point in time. But the average acceleration is change over. And just think about average. Average is something divided by. Again, with the sign convention, I might be traveling in this direction to a stop sign, but my velocity and my acceleration are both working against me because I've pressed my brake. So I might be slowing at an acceleration which is making my velocity decrease. Okay, so instantaneous. Instantaneous means that I have a function for the entire path that I took. Okay, I have a function for the entire path. And so if I have a function and I want to know at 3 seconds, where am I positionally, then I can take my position equation, plug in 3 seconds, and I can come up with, I'm at 21 meters. Same with velocity and same with acceleration. Okay, so I can just go through those and get those instantaneous values. So let's talk about that relationship. So I like to start, if I'm working homework or examples, I like to start with this picture right here, where I have acceleration, velocity, and position. And actually the way I start is, everybody pretend like you're in your car, you're driving to Oklahoma City. you get onto I-35, and what do? You put on your cruise control. So if your cruise control is on, your acceleration is 0. Okay, it's 0, which means your velocity is constant. So it's just a function of time, and your positional change is linear. It goes from constant to a function of time. So for 1 hour, my acceleration is 0. My velocity is 80 miles per hour, and in that 1 hour time, I've traveled 80 miles. And that's how I try to remember, am I going to be integrating or taking a derivative? Which way am I going? So I kind of put this in my brain. Okay, so if we integrate our acceleration with a function of time, we end up with our velocity because we're just finding that area under. It's just like having our load. If we had a uniform load, we find the area under that load. That gets us our shear, which is diagonal. Okay, if I integrate velocity with respect to time, I get an equation. I get where I am positionally. So how do I know whether I integrate or take derivatives? I go back to, I'm driving down the highway, 0 acceleration, constant velocity, linear change. Now I know nothing, 0 degree, 1 degree. I know I integrate in order to increase that degree, and I take a derivative to decrease that degree. Okay, so that's how I remember which way I'm going. Okay, so here's an example. Here our position is given by a equation of 3t squared plus 6t minus 12 meters. Okay, so if I am wanting to get to velocity, I can see that from that position, I'm going to be going linear. That's going to be taking a derivative. At 10 seconds, I am at 348 meters. So how can I get to the velocity? I can take the derivative of my position. There's the derivative. There's my velocity equation, plug in 10 seconds, and here's my velocity at 10 seconds. This is not the average. This is not the average speed. It's at 10 seconds. I can take my velocity equation. I can take the derivative of that, and voila, I have an acceleration equation. So at 10 seconds, this is what's happening. This is where I am in my car. This is how fast I'm going. This is my acceleration. Okay, so it's important to talk about boundary conditions, because we don't just always integrate from 0 to time and 0 to position. As we can look at these charts, I can see that my position is starting maybe behind the starting line. So think about if you and I are running a race. Clearly, I'm going to need an advantage. So I'm going to start on the line. So my position right here would start at 0, 0. But because you're so much faster than me, I'm going to make you start 20 feet behind. You're going to start back there, so that I have a little bit of an advantage. And that would be a boundary condition. You would be starting at -20, not 0. I would be starting at 0. So I guess in this case, it's actually -12 if you look at the equation. So you would be starting 12 meters behind me, okay? 12 meters behind me. So you have to be very careful with boundary conditions as you're doing your integration, okay? So at 10 seconds, this is exactly what is going on with that particle, with that car, with that runner, with the rocket, with whatever, okay? Boundary conditions. So now we're going to be integrating acceleration to get to velocity. Before we did derivatives. And if I integrate 6 meters per second with respect to time, I can see that, okay, at time 0, I've already got a velocity that's happening, okay? I've already got a velocity. So note here, okay, note here, that our velocity is initial velocity to final. It's not always going to be 0. In this case, I know that I'm already starting at 6 meters per second. So as I integrate 6 with respect to time, my velocity is already starting at 6 meters per second to a final velocity. So I have to make sure I use those boundary conditions so that I get the appropriate equation. I can now go back and check. Well, at time equals 0, I can see that my velocity is 6. Yep, that's exactly what my graph says. So you can check to make sure you're using boundary conditions correctly. Okay. I also note I am going to put my velocity in terms of time. I'm going to leave this as a v and this as a t so that I have a velocity as a function of time equation so I can integrate that to get position. Okay. So here we go. I'm going to integrate velocity with respect to time to get my position. Okay. So here's my generic position velocity integration. Boundary conditions. I'm already at -12 meters is where I'm starting. So I have to make sure that I have this boundary condition down here. Okay. integrate, make sure I do all of my algebra correctly. Again, I get an equation. I can plug in time equals 0, and I can make sure that I have that boundary condition correct. Okay, so the next thing we need to talk about is, well, how do I know if I've changed direction? So what if I am driving to Aspen to get my coffee and then I'm coming back home? How do I know that I changed direction in there? What am I going to have to do when I pull up to Aspen? I'm going to have to come to a velocity of 0. We can only turn around, well, unless we're fancy drivers, I guess, but we can only turn around if my velocity comes to 0. So when I have a velocity equation, it's super important for me to know when velocity is 0, because I might, in this 10 seconds, have to go this way and then turn back around and go that way. So my total distance might be a lot larger than what I'm anticipating. So once we get a velocity equation, so I can take the derivative of position to get the velocity, I can now set my velocity equal to 0, and I end up with t equals 2. Now it actually equals plus or minus 2, but we don't have negative time. Okay, we're not Doctor Who. We cannot get into, anything to make us go backwards in time. So in this case, we're going to have 2 seconds will be where we turn around. So when the velocity is 0, the particle is changing directions. It's important to note in this case, there's only one value of t. Make sure you understand that if it is t squared, I will have 2 roots of time. If I had t cubed, it would be 3 roots of time. So make sure you're checking for all of those, okay? So now that I know that I've turned around, once I'm looking at my position equation, and I'm going to try to find my total distance, not just displacement, final minus initial, but the total distance, I'm going to have to find my position at time equals 0, at time equals 2, because that's where I've turned around, and then time equals 10. Okay, so I'm going to be checking all of those things. That's where I turn around. So if I want to know how determine the distance traveled by the particle when t equals 5 seconds, then I need to plug in 0, that's where I've started, plug in 2, that's where I've turned around, and then plugged in 5 so I can get my total. So my displacement would be 16 minus 6, which is 10 meters. But if I look at my total path traveled, it's actually a lot larger than that. It's actually 16 plus 2 and 6 plus 2, because it would be 6 minus a negative, okay? So make sure you understand distance, displacement. Displacement is 16 minus 6. Total distance is all of that added up, 26 meters. So always check, have I turned around in here? What time is my velocity equal to 0? Okay, so and then this is all just algebra you can go through, but it's super important to figure out when you're turning around, what it's looking like. I really kind of like math, so I like to sketch everything out. But what's important to note here is my velocity right here is 0. That's going to coincide when I'm changing my direction. Okay, when I'm changing my direction. So if we were to rewrite these equations, so right now we have acceleration and velocity and time. Those are the only 3 parameters we have. We have velocity, position, and time. That's it. If we can rewrite both of these in terms of dt, then I'm going to have dv over a and ds over v. And dt has to equal dt. So we're going to rewrite, and now we have an equation that is not a function of time, but a function of position. So the biggest questions we ask ourselves is, am I looking at a system of equations that's a function of time, or am I looking at a system of equations that's a function of position? Because there'll be 2 different techniques that we're going to be using to solve. So here is our variable equation that is a function of position. Our acceleration is a function of position. Okay, so kinematic equations. This is it for chapter 12. Well, there's going to be a few more things that we do, but these are kinematic equations, and you may recognize these from physics. Okay, so we have function of time, we have function of position, but if we have constant acceleration, then we can integrate with respect to constant acceleration. And when we do that, we end up with these 2 equations, and you probably do recognize these from physics, where we have v equals v naught plus constant acceleration times time, and our position is s naught plus v naught t plus 1/2 constant acceleration times squared. We can also integrate the function of position equation, the ADS, and come up with v squared equals v naught squared plus 2 s minus s naught. Okay, so this is our displacement in here. This is displacement. This is not the total path traveled. Okay, so we have the equations we can integrate. We have the equations if our acceleration is constant. So just a review: variable acceleration, function of time, function of position. So first question you ask yourself, is this variable acceleration or constant acceleration? If it is variable, is it a function of time or is it a function of position? That's how you get started on problems, okay? If it's constant, then you can use these easier equations, okay? The easier equations. There is an equation sheet available in course information and in your homework module. And as I go through all of these equations, I'm going to make sure to pop up part of your equation sheet so that you can see what part of the equation sheet we are learning about so that you can use the equation sheet as you're doing your homework, because this is the equation sheet that will be on all of your exams. Okay, this will be what you get to have on all the exams. So this is what we've covered so far. So now you can stop this, pull up the example videos, and work through some examples.